Bismillah ar-Rahman ar-Rahim. Welcome to Dar Scholar. We are السبت 30 مارس 24 بالجزائر, or in English Saturday the 30th March 2024 in Algeria. So we are now in chapter 2. This is the first video for chapter 2, Systems of Linear Equations. But before to proceed, I have to apologize for not having uploaded any videos during almost 2 months and a half, because I went through all kinds of problems. I live like in a hostile environment. I am fine now, but I went through really a tough time. The second problem is that when I was a teacher in the university, I used to teach this module one lecture and one tutorial per week. So due to lack of time, I had only to teach the basics. But now I am on my channel, I can organize better my course and deliver more. I have never taught this module in this way, so more details. And that's why I had to, of course, to revise my notes, to update them, to reorganize them. And this, of course, takes time. So I apologize again for that. And I think in future, between each chapter, I will take 3 weeks, 4 weeks to revise my notes. I will try not to exceed 1 month between each chapter. So now let's focus on the chapter. So introduction. First thing, systems. What is a system? Systems of linear equation, of linear equations. So the main goal of this chapter is to solve a system of linear equations. Let us see 2 examples. The first with 2 equations. For example, x plus 0.7 y equal minus 1.5 and 2.3 x plus 4.5 y equal 3.9. The second example, and I will use these 2 examples along this chapter. When we study the methods to solve them, we will come back to these 2 systems of equations. So there are just 2 examples. I have randomly chosen them. The second system of 3 equations, 2.5 x plus y minus z equals 1.5 x plus 2.9 y plus 1.2 z equal minus 4.3. 3.7 x plus 5.8 z. So here there is no y, equals 5.2. So this is a system of 2 equations, and this is a system of 3 equations. And the unknown here are x and y, and here the unknown are x, y, and z. And observe that all the equations here, all the equations are linear, are linear. That is, there is no x square, y square, or x times y, or I don't know, sine x or cosine x, logarithm, and so on. It's very simple equations. Not like in the first chapter, the equation is non-linear. Here we have several equations, but each equation must be linear. The second point to note here is that the number, I note here NB, but it means number of the known variables, variables is equal to the number of equations. Otherwise, we cannot find x and y, or x, y, and z. We cannot find the unknown variables. So this is a second condition. And third note, not a condition, just a note, that when you have larger systems, for larger systems, it is better to note the unknown variable as x1 with an index, x1, x2, etc., xm, for a system of m equations. For a system of m equations and m known variables. So this is a system of linear equations, but it's better to manipulate and note or denote a system of linear equations using matrices. So we introduce here matrix notation. So the second point, matrix notation. The two examples, we write them in a matrix form. So we write here a matrix 2 by 2, and we put in the matrix the coefficients of the variable. So for x, we have 1, 2.3, and for y, we have 0.7 and 4.5. Dot x and y. So the inner product of the matrix A with the vector x gives us the vector B, or it is also called, in engineering setting, it is called the load, and x is called the answer or the response of the system, the load and the response of the system. But in general, you just call it the image. Vector B is the image of the system. So minus 1.5 and 3.9. This is the first system, and our goal is to find the vector x. So this is more clear and more flexible also to manipulate than the classic notation. Maybe you have seen that in high school. That it's better to manipulate a system with the inner product of a matrix with a vector. I'll come back later in this, just after this section, to the inner product, to the meaning of the inner product. So it's the inner product of a matrix A with x. It gives us the vector B. For the second, this is the first system. For the second system, we have a matrix 3 by 3. and the coefficients 2.5, 1.5, 3.7. Here we have 1, 2.9. Here we have no y, so 0. And minus 1, 1.2, and 5.8. And 5.8. Okay, let's check again. Yes. Inner product with x, y, z. And it gives us the vector, the image vector 1.5, minus 4.3, and 5.2. And we here also have to find x. A is given, B is given, the load or the image, and we are looking for x. This notation actually defines a linear mapping, a linear mapping that associate the vector x to the vector b. And the goal is to find the source, knowing the image. You know the image, but you don't know the source. You can express a system of linear equations as all who can see it as a linear mapping where the source is unknown, is not known. So, before to write the problem, to generalize, because this is 2 and 3 equations, to generalize it, let us first explain or revise in more detail the inner product. Normally the inner product, the linear algebra is taught before numerical methods, but we have to revise the basics in order to solve, to understand how to solve a system of linear equations. So, what is the inner product? And we have seen that also, I think, in practicals 2, I think, practicals 1 and 2, when we revised the MATLAB language. I have done like a crash course for MATLAB. Check the 2 first practicals for matrices. So inner products. First of all, definitions. We will define first a vector, inner dot. You can say inner product of or dot. So we start with vector dot another vector, u and v, with u and v belonging to Rm, to the space Rm. Means the dimension of the space is m. There is m components in u and v, and all the components are real numbers. That's what it means, Rm, or space Rm. When we do the dot, the inner product of u and v, we obtain a scalar that is, by definition, equal to the sum of up, the p component, times a vp. So up and vp are in R. We do the multiplication of the component up and vp, and we add p from 1 to m. That is u1, v1, plus u2, v2, etc., until the last term, vm. So this is the definition, very simple, it is a scalar. Then the inner product of a matrix with a vector. It gives us a vector. So let's say U equal A times W, with A is a matrix in Rmn. So here the space is of second order. It has two dimensions. The first dimension is M for the rows and N for the columns. And W belongs to Rn, Rn, the same dimension as the number of columns, and U belongs to Rm. So when you do the inner products, here M times N, here N. So there must be the same number of columns as the number of elements in W. Or you can say also that the index, the second index of the first matrix must cross the same number of elements as the index of W, N. And the first dimension for M. So it must correspond to the number of rows in A. This is a condition for the size. Otherwise, the inner product has no meaning. And its definition, how to calculate it, is the sum of A, IP, so I for the number of rows, not the number of rows, I mean the row index, for the row index, and P for the column index. This is a real number times WP. So P crosses the same range in the two operand, in the matrix and the vector. With P from 1 till N. And what this gives us? It gives us the ith element or the ith component of U, UI, with I from 1 to M. So if you replace I equal 1, you get the first element. So for example, U1, you get A1, 1, W1, plus A1, 2, W2. So P is replaced by 1, the second term by 2, and so on till the last term, A1, M times WM. And we have here the first component, so it must be the first row, always the first row. If you change the number of rows, you change the number of if you change the element of U, the index of the element in U, you have to change the row index of A, according to the formula that define the inner product of a matrix with a vector. You can also interpret the inner product in another way by using a column. So you can. So this is the first interpretation, first definition, using real numbers, but you can also use a column. You can write U, the vector U is equal the first column times W1 plus the second column times W2 and so on until the last column, WM. The definition, or you can write it like A, P, times WP, with P from 1 till N. All same. And we can say here that actually the columns of A, the columns of A span the space Rn. The space Rn. And the components of W are the coordinates of U of the inner product in the span. So, and the components of W are the coordinates of the inner product A W. So the column of the matrix acts like a span of the image space. Okay, you can see that in two different ways, using real numbers or using columns. Observe here it's a vector, while here it's an element, because here we use real numbers, and here we use a column. So a column is a vector. So it must be here a vector, not a component. That's for the inner product of a matrix with a vector. Let's move to a matrix by matrix. I beg your pardon here, I've made here an error for the indices. So the columns, the number of columns is n, not m. First column, second column, the nth column. And the first element of W, second, the nth element. Because P goes from 1 to n, not m. So here should be n and n, not mm. Same mistake here. It's n, the nth column of A, the nth element of W. So a silly mistake, but here it is correctly written 1n. And here also again 1n. And here the columns of A span the space Rm, not Rn. Because the vector U, the image, belongs to Rm, not to Rn. So the mapping is from W to U. This is the mapping of A, matrix A. Matrix A define a mapping W to U. W belongs to Rn. It has n element, n columns of A. And the image space that contains the vector U is Rm. Rm, not Rn. So, silly mistake, I beg your pardon here. And that's it. The inner product of two matrices, A, B, A dot B, with A in Mn, and B the same N by L. So here the same N, and C in RML. So for the dimension, here M, N, and here N, L, correspondence of the dimension. The second, the number of columns in the first matrix must be equal to the number of rows in the second matrix. And we are left with M and L. It goes to C, M times L. And what is the definition? Definition, also we can see it in two ways, using real numbers, the component ij of C, the element at the ith row and jth column, equals by definition the sum of the first index go to the first matrix, and the second index go to the second matrix, but to the columns. And here we have P. So we sum over P. P from 1 till N, to N, from 1 to N. Here real numbers. To obtain the element the element ij, Cij, ith row, jth column. So you can see the inner product in this way, or so here you obtain an element in C at the ith row and the jth column. But you can see it also by columns, like we have done with the previous inner product, a matrix with a vector. So we can write that this way. The jth column of C, by definition, is equal to the matrix A, the whole matrix, dot the column J. So this is a vector. The jth column of the matrix B is a vector. You perform the inner product with A, you get the jth column of C. So each column of B will generate the corresponding column of C. That's why the number of columns in C and in B must be the same. L, L. So let's write it. We obtain the whole column, not just one element of C, a matrix C. You can see definition in two ways, by a real number or by a column. And that's it for the inner product. You can also check in MATLAB or Octave, MATLAB language, they don't use dot, they use multiplication. Multiplication of matrices. It's equivalent. But because MATLAB doesn't deal with a vector, the meaning of a vector. So this is more general and more formal. In MATLAB, it's limited to only matrices. So let's see an example, a concrete example. So let's see a concrete example. For example, the matrix A equals and the vector W equals the same number of elements as the number of columns in A. So for example, 0, 1, 0, 2, and 0, 3. And we get the result U equal A dot W. What we do, we first put the element of the matrix. 1, we leave space. 2, we leave space. And for the second element, 0, 1 plus 0, 2. Second element is obtained using the second row of A, 0, 3. And for the third element, minus 1, 3 plus 0, 5 plus 2.7. And then we replace the elements of W in the sum. So here 0, 1, first term, 0, 2, and the third element 0, 3. And we repeat the same vector for each row. And this will give us the vector U, the inner product, which I have already calculated, 1.4. You can check, of course, with your calculator, 0.14, or with Octave, 0.78. I advise to revise the practicals if you have forgotten the two first practicals dedicated to Octave. So this is how to calculate the inner product using the definition. You can also see it in this way, because we have seen that the definition of a matrix with a vector or a matrix with a matrix can be seen in two ways. We can also see it like this. The first column plus second column plus the third column. These three columns span R3, space, image. Because here M is equal 3. Matrix A is a mapping that associates a vector X to, here not X, is W. Vector W to the vector U. The vector W belongs to R3, and U also belong to R3. So you can see that as a mapping. This is the image space. The space that contains all the images by the mapping. This spans, we will see later what is a basis. The span has not to be a basis. It depends on the matrix. We will see that later. So let's say here, just span, it's span. So you can express any vector in the image space using the columns of the matrix. So here 1, the coordinates of the vector 0, 1, of the vector W. The coordinates, the elements of W are the coordinates of the vector U in the image space. And you obtain, of course, the same result. So both are equivalent. But this is more easier when you use a calculator. So this is the first example. We can go further, of course, and let's better do another example with matrices. So that's the same matrix A, but the matrix B with 3 by 2. So 0, 5, 0, 0.9, 1.8, minus 1.6, 4.1, minus 2, this is minus 2.5. And we want to calculate C A dot B. Here it is better to use by columns, to work by columns, not each element of C. C here should be, because this is 3 by 3, and here is 3 by 2. We should obtain here 3 by 2. So we do the product of the first column of B to obtain the first column of C, and then the second column will generate the second column of C. That's better than calculating every element of C using CIG. So here it's better to work with columns. First column, I write the first matrix. So I put the matrix A, all the matrix, and I leave spaces for the column of B. Then I put the columns of the B, the first column. And I repeat it at each row. And I obtain the first column of C. So 7.7, 0.77, 4.66. And for the second column, same, I put the matrix A, and the second column of B. And I repeat at each row. So I get minus 0.9, minus 0.09, minus 2.62. And this will, I put the two columns here, the matrix C. So this is how we calculate the inner product of two matrices using a calculator, hand computing. So yeah. And then that's it. Very simple to apply the definition. And again, normally you have studied that in linear algebra, but it's nice to revise it again for this chapter, if you have forgotten it, maybe. So properties. So we have seen definitions, examples. Now properties. There's some properties. Properties are actually theorems, but I will not give the proof, or otherwise it will take a long time. I will do linear algebra, not numerical linear algebra. The first property, the transpose, when we use a transpose. The first property, when you have the inner product of A and B, but the transpose of it. We can easily show using the definition of indices, the first definition using IJ. You can easily check it's the inner product of B and A, so in the reverse order. So T goes to A and B, but the inner product in the reverse order. The second thing is when you swap, when you have, for example, a vector U, inner product A, inner product V. So we have here a vector dot another vector, it's a scalar. But if we swap U and V around A is like a pivot, we have to transpose A. So A becomes T, transpose of A by U. Now if you have, for example, let's write it here. For example, you have here 2 elements and two by 3, and here you have 3. When you transpose, when you swap, it becomes a matrix 3 by 2, like this. And you have the vector of 3 elements comes here, and the vector with 2 comes here. When you swap, so this is also a useful property of the inner product. The third property is when you want to scale a matrix. For example, you have a matrix A, let's say A1, 1, 2, 1, 3, 1, first column, and the second column and the third column. And you want to scale each column by a number, by a real number. For example, the first column by A times A. The second column times B, scale it by B. And the third column by C. So you have a matrix where each column is scaled by a different number. You can write this matrix in this way. The matrix A, with its 3 columns and 3 rows, the inner product of a diagonal matrix. A diagonal matrix, all its elements are 0 except the elements on the diagonal. You put here A, B, and C. And here 0. So these two are equivalent. So if you want to scale a matrix, column by columns, you have to multiply it or to dot it to perform the inner product with the diagonal matrix. Such that the scalars are carried by the diagonal. So this is a diagonal matrix. And if you want to scale by row, the diagonal matrix, the same, should come first. So with the diagonal matrix, then the matrix itself. So the fourth point is problem formulation. We have seen the meaning of the inner product. We can generalize the examples we have seen in the second point to state the problem formally: A dot x equal B, find x. This is our problem. to solve in this chapter. Where A is a square matrix, means the number of columns and the number of rows are the same. It belongs to Rm by M. X and B both belongs to Rm, and the mapping is from X to B. B is the image. And the goal of the problem is to find the source. So this is in matrix form. Here is expanded in tabular form, first column, second column, and the mth column. And the rows goes from 1, 2, 3 till m. The vector x, its components, the vector b, its components. And the goal is to find the family xj, j from 1 till m. We say family or the indexed set. In French, often in books in French, we say the family, la famille des éléments. So, la famille des éléments, or indexed set. So this is the goal of this chapter. Or in indexed form, indicial form, the product A and X, AIP, XP, the sum is over P from 1 till M equal BI, I from 1 till M. It's the definition of the inner product, as we have seen in the previous point. And the goal is to find the family xj, j from 1m. These three formulations are equivalent. And the methods, there are actually two categories of methods, direct methods and iterative methods. Because this is a foundation course, we will study only direct methods. Iterative methods are normally taught in numerical linear algebra, in a module. Numerical linear algebra has several topics. Solving a system of linear equations is the main topic, is the most important topic in the numerical linear algebra. And we will focus on direct methods. There are two techniques, Cramer's method and Gaussian elimination. LU decomposition and Cholesky's decomposition are a variant of Gaussian elimination. LU means lower upper matrices. We decompose the matrix A to a lower matrix and an upper matrix, and then we solve two systems. We will see that in detail, of course. And Cholesky's method is suitable only when the matrix is called the definite positive. It has some property to make it definite positive. We'll see that the meaning later, but it's not for all matrices. Gaussian elimination and LU decomposition for any matrix, symmetric, non-symmetric, definite positive or not. But Cholesky, the matrix must be symmetric and definite positive. And definite positive matrices are very important particularly in mechanical engineering, where we study the simulation of structures and solid in elasticity. The matrices we build there are definite positive. So 4 methods. I have never taught Cholesky's method when I was the teacher. LU decomposition, I think I have given only an overview to my students. So here I will detail more for the direct methods. Another topic also important is matrix conditioning. The matrix might have some, we call that ill-conditioned. Matrix might be ill-conditioned, and the results, you cannot trust the results. We will see that also later. Normally this is more advanced, but it's okay, it's not that advanced. Even numerical linear algebra, when I say advanced course, it doesn't mean a PhD or master level. You can teach that at bachelor level. But you need foundation course. You need a first course. And then you go further, numerical in algebra, partial differential equations, what else? Optimization are advanced courses in numerical methods. You need first a foundation course. So this is what we will study in this chapter. See you inshallah next time. Peace.